This video is a follow-up to the last video I made called Pro Tip Don't Get Behind. In that video, I showed two homework problems I had been working on in my functional analysis course, and the first problem I wrote, I don't think there was anything that was false, but it did not have all the details there, so I did not get credit for it. But the second problem I did get credit for, although I had to fight tooth and nail to get the credit, and I did receive help from the class, which, you know, I'm grateful for, but I kind of want to just present one problem with no issues and just finish it in 10 minutes and just sit down. That's all I really want in my life at this moment, because I'm tired of getting up in front of the class and making an ass out of myself, and it's getting kind of annoying. But I shouldn't be so upset, and I'm not that much upset. It's just, I just want things to go well. If you put in this much effort, I should at least have 10 minutes of just let me get whatever. I don't want to talk about it anymore. And I should probably mention that problem I presented needed to be tweaked a little bit in order for it to work. There is a slight caveat that needs addressed, and I'll probably make a video on it in the near future before I forget the total solution to it. But it was rough, though. I was up in front of the classroom for an hour and 20 minutes presenting two homework problems, but it was mostly just the one homework problem that took up the majority of the time. But I did get credit, so I'm a happy camper, all things considered. So what I want to do is talk about the first homework problem. So if you haven't seen the video, I would recommend watching it, but you don't really need to see it because I'll just go over it here again, but it is worth watching, I guess. So the first problem says, and I'll explain what this is here in a second, just bear with me. The first homework problem is a pretty benign statement, but it's not as easy as I thought it was going to be. Maybe I'm just an idiot, but you have this convex body K, you have 0 that's in the origin that's in the interior of K, and we assume that the radial function of our body is equal to its support function. So if you're not familiar with the radial and support function, they are two important functions that show up there in convex geometry. They're two very important tools that help us characterize a body. So here we have this this convex body K that I've drawn here, and the origin is in the interior, and you pick some unit vector E. So E is some vector on the unit sphere. It points in some direction, and you want to evaluate rho at E. So what does rho say? Rho says, okay, how much do you need to scale E by in order to touch the boundary of K? And that scalar that you choose here to get to this point on the boundary is called rho of E. So what does the support function say? So the support function says, okay, look at parallel lines or orthogonal. Well, if you think of an orthogonal subspace, you have this vector, you look at the orthogonal subspace that passes through the origin, and then you look at affine transformations in the direction of E, or translations, I should say, if I want to, whatever. So you move the body until eventually you just barely touch the boundary of K, and if you go out any further, you leave the body. So that amount there is what you need to scale E by in order for this perpendicular line to just barely touch K, gives us H of E. And it should be obvious from the picture. I mean, you have to show it rigorously, but it is a fact that the support function is bounded below by the radial function. And here we're assuming that the two are equal to one another. And if they're equal to one another, the claim is that our convex body K must be a ball. Which, if you think about it for a second, it actually makes a total sense. But showing it is, I don't know if I'm just dense, but it seems to be harder than it seems on the surface. But either that or I'm just not seeing something, which is more likely the latter. So after doing some digging, I have this proposed solution. I'm a little bit scared of it, and you'll see why here in a second. But let's just go through it slowly. What I want to use is this inequality. It's called the Blaschke-Santalo Inequality, and it needs this notion of a polar body K. So the polar body of K, which is denoted K circle, is defined to be the all vectors y and Rn such that the maximum of the scalar product of x and y, where x is in k, is bounded above by 1. So this gives you some convex body in our space Rn, and it's referred to as the polar body of k. This is another way of writing it, and I thought maybe it might be useful. I looked up the definition of K-circle, and they had this written there, so I wrote it down just in case I needed it, but I don't really think I will. And then we have these two properties about the radial function of the polar body and the support function of the polar body. And it says here that we can express those two functions in terms of the radial and support functions of k. And I have both of them written, but this is the only one I really use. The radial function of the polar body is equal to 1 over the support function of k. And that's all good and everything, but I have this assumption that rho of k is equal to h of k, so what I can do is substitute rho of k in for h of k and get this guy. And then through simple algebra, we see that rho of k circle is equal, rho of k circle times rho of k is equal to 1. And this is where kind of like the real problem starts. Because I want to use Blaschke-Santalo inequality, which I'll show you where that comes into play here shortly. But we need to use the Cauchy-Schwarz inequality. So what I'm going to do is I'm going to take both sides and raise it to the n over 2 power. So n over 2, n over 2, 1 is just 1, so we have this guy. And then we multiply both sides by 1 over n. 1 over n. Okay. Then we will integrate both sides with respect to E, where E is a unit normal vector on the unit sphere. So we take 1 over n, we integrate it, put it over here. It's just a constant, so it pops out. So you get this integral dE over unit sphere. And then here you have equals to 1 over n integral of the product of my two rows, which show up here. And this is where you want to use the Cauchy-Schwarz, sorry. So Cauchy-Schwarz says square this guy, split up into two integrals raised to 1/2 power, which is what we have written here. And then I can push in this 1 over n inside here and inside here, because it is 1/2 power here, 1/2 power here, and is just square root of n times square root of n, and is a non-negative or positive number. So we get this guy. And the reason that this guy is interesting is because we have this function, or not this function, but this identity that was developed in our convex geometry course that says that this guy, if you have 1 over n integral Sn minus 1, rho of some body, convex body, raised to nth power dE, then this guy will give you, what does it give you? It gives you the, the volume of the body determined by K, which in this case I've written K circle, but it's a convex body. You can substitute in the volume. So this guy gives you the 1/2 power of the n-dimensional volume of the polar body, which is written here, and this will give you the volume, n-dimensional volume of K, which is written here. And everything's raised to 1/2 power. So this is what we have. Now, why do I care about that? This is where Blaschke-Santalo comes into play. So that inequality says that the square root of the product of the two volumes is bounded above by the n-dimensional volume of the Euclidean ball. And we only have equality if K, our body K, is an ellipsoid or a ball in this case. A ball also counts as an ellipsoid. And usually this inequality is written without the square root. They just square this side, but it's okay. We can take square root. And then how do we write the n-dimensional volume of the ball? Well, this is just 1 over n integral Sn minus 1 rho of what? Our body B raised to nth power, but the radial function for a ball is identically equal to 1, and 1 raised to n is 1. So this guy reduces to 1 over n integral dE Sn minus 1. And this guy is exactly what we had written here. So we have this inequality, this less than equal to this, less than equal to this, which means that they have to be equal. And then by this theorem, we know that K has to be an ellipsoid. And the only ellipsoid where the radial function and the support function are identical to one another is the ball. And that is more or less how you finish up the proof. And it's kind of a slick little thing here, which if you didn't know about that theorem, which we currently don't know in the class because we didn't cover it, I looked up the theorem on the internet. It's kind of... What that means, essentially, is that I have to prove the theorem. And when I went on the internet to look up the Blaschke-Santalo Inequality, I found a ton of resources that cite it, but none of them prove it. And I basically spent the whole night trying to find a proof of this inequality, which, according to the history, it was proven in dimensions 2 and 3 in 1917 by Blaschke. And then it wasn't until 1949 where all dimensions were taken care of, which is after a ton of Googling, I found the paper. And it was written in a Portuguese math journal. And what that means for me, this is the original paper by Santalo, hence the name Blaschke-Santalo. And what that means for me is that I have to, if I want to prove this theorem, I need to translate all this Portuguese into English. And you know what? I just want one homework problem that takes 10 minutes to prove, where I don't have to translate from Portuguese into English and just get my credit and move on. But I know I'll have to sit down and do all this. And after reading this, I was like, man, there's got to be an easier way to prove this. I'm working harder and not smarter. But I don't know, man. I mean, the paper's not that long. It's 7 pages, essentially. The 8th page is just nothing. It's bibliography. But still, it's like... Let's make life easier in the last week of the semester. Let's not do things unnecessarily. Let's not choose the hardest path. Let's do the path of least resistance. How about that? But anyway, I have to be grateful that I at least found the paper that proves the inequality. And what annoys me a little bit about this is that I just foresee myself bombing in front of the classroom, that I have been bombing for the past couple weeks of trying to just prove stuff. And, you know, I've gotten to the point where I've developed a thick enough skin where it doesn't bother me, but I do relish the day where I just want to be up there, speak for 10 minutes, everything goes well, and then I sit down and I get my credit. That hasn't been happening for the last month, maybe 2 months. In fact, you know what it reminds me of? It's kind of a tangent, but I guess I'll tell the story. When I was in middle school, I really got into rock and roll music. And that was also the time when like Guitar Hero was really popular. And because of that, I really wanted to learn how to play an instrument, and I learned how to play guitar. And I recently got back into it, playing guitar. I haven't really played in a long time. But I was looking up videos on YouTube of famous guitar players and rock musicians playing their stuff in front of crowds. And I discovered the 1985 Live Aid performances from a myriad of different musicians. Like, I know Eric Clapton played there, Queen played there, a bunch of other people too. But one that I found that played at Live Aid 1985 that I was surprised I hadn't heard of before was the rock group Led Zeppelin, which is like the biggest rock and roll band of the 1970s. Surely, if you haven't heard of Led Zeppelin, then what are you doing with your life? And I'm not like a huge Led Zeppelin fan, but I do like their music. And they're pretty talented bunch of guys. Anyway, so they reunited after disbanding like 5 years prior, for Live Aid to perform 3 of their songs, and it was like a huge deal. Like millions of people tuned in to watch it on TV. I don't know how many people were in attendance that day in that giant football stadium, but it was a massive event. And then I watched it on the internet on YouTube, and I read the description, and it said, "This is the infamous Live Aid performance from the reunion of Led Zeppelin." I was like, infamous? It's like, how bad could it possibly be? And then I watched the whole 20-minute performance on YouTube. If you haven't seen it, I would recommend watching it, but it is really cringy. Like, I told everyone about this video after I watched it because I could not believe just how unbelievably bad it was. So if Led Zeppelin can bomb in front of millions of people, then I can bomb in front of like 4 or 5 people in my math room. Like, I don't care. That's like, no one's going to really watch it. Like, if they have that thick enough skin, like if Led Zeppelin can bomb, then surely, you know, everyone else can, because that was a spectacular disaster. Just nothing went right. I'm pretty sure the guitar player was stoned out of his freaking mind. Like, I'm laughing at it because I can sympathize. Like, I don't want to say I know exactly how they feel, but I've like experienced maybe like at least 1%, I would say, of what they must have felt on that dreadful evening. But the crowd didn't really seem to mind in the video, which I guess is good. But anyway, that was a little bit off topic. But having been bombing in front of the classroom this amount of times over the past month, the video was kind of like, I'm not describing it very well, but it was a bit sobering. Like, I watch it, I was like, okay, it could be a lot worse. I guess that's the big takeaway. It could have been a lot worse. And I appreciate, you know, watching it. I've probably seen the video like 10 times now. It's such a great video. Especially if you're someone that's experienced a fraction of what they did. Anyway, that's enough rambling for 17 minutes.